Okay, good afternoon. Bill Gillespie here again. I guess we'll go ahead and get started on another session in our course on modeling of categorical data. What I wanted to talk about today, at least for most of it, we'll be talking about model evaluation, and I wanted to focus primarily on methods for categorical data, though some of the methods we'll talk about are applicable to a broad category of data, including continuous data. And so what did I want to say about that? Sorry, I'm going to get my brains together for the course again. But the main thing I want to focus on are those things that are unique to the problem of dealing with categorical data. And as a preface to this, I was going to give you at least one perspective on what a Bayesian model evaluation and comparison process would look like, and actually give you what a view anyway of a typical Bayesian model development process and how the model evaluation fits into this. And the approach I'm presenting here might be somewhat different from other approaches you've been exposed to that may involve a great deal of model comparison and rejection. There's still a model comparison and rejection process here, but the notion here is that I guess the one difference is you're maybe more likely to accept rather than reject than you might in using the more classical sort of model selection process you may have seen, particularly for covariate selection and population modeling. So what I'm calling here a typical practical Bayesian model development process would look like one where you start out by proposing an initial model structure based primarily on available prior information. Now, that's the ideal, to really base it on prior information, but as I comment here, realistically, exploratory analysis of new data is also going to influence that process. Now that, to some degree, puts some of your formal probabilistic inferences at risk by looking at the new data at the same time as you're constructing the model, but depending upon the problem, it might not be a big risk. So you start out by proposing a model. You then go through a process of assessing whether that model is consistent with both the data and with prior information. And so when I say this, I mean you're going to be assessing it after you've actually analyzed the data. So we will take the model we've proposed, we'll then apply it to the data. So we're getting our posterior distributions of our various parameters. And we can do posterior predictions of potential new observations, and we're going to compare those predicted observations to the observed data to basically assess whether the model is capable of simulating data that behaves similar to the observed data. And this falls under this general heading here of posterior predictive checking. So we're going to take a look at some methodologies for that. The other side of this that we're not going to go through in detail but should also be part of the picture is to assess whether or not your model inferences, your predictions, and the values of your model parameters and any other derived quantities are consistent with other knowledge. In particular, this would be other knowledge like the prior information upon which you based your model and any other any additional evidence that you may have. So you can ask questions like if you've constructed a model where some of the model parameters are thought to be quantities connected to actual, say, physical quantities in the system you're modeling, you might want to compare them. So, classically you might compare a volume that you believe to be a volume of a particular physiologic space. You would compare what you know about the true volume to the model estimated value, and if it's very far off, well, that might make you skeptical of your model, for example. Okay, but the whole point here again is you're going to be doing comparisons both with the data that you're modeling now as well as any prior data or information. What we're going to focus on in our discussion is really the first part, which is comparing with the data via posterior predictive checking. In addition, you'd like to do things like assess sensitivity to potentially influential assumptions. And in the Bayesian context, the place where that gets unique is we're now introducing prior distributions, which could be influential. And we may want to assess whether, just how influential they are. And if they are very influential, then we have to look closely at them and assess whether we really believe our prior assumptions and prior distributions. And then finally, if any deficiencies are discovered through that process that might adversely affect any important inferences that are going to be made based upon that model, then you should explore model revisions and basically go right back up to the top of this process and start again. So we still have an iterative model comparison process, but it's perhaps a little bit different than the way you may have thought about it and the way it's often described in the context of population PK modeling. Continuing that, then once you feel you have a suitable model, then of course you'll use that model for any pre-planned inferences that you may have. And then optionally, there will often be some additional hypothesis generating activities in here. So there may be some additional data mining efforts to explore the influence of covariates that weren't considered in your original model. And you may go on to explore alternative model structures that also weren't considered in your original analysis, particularly your original sensitivity analysis. And during that process, you may discover that some model appears to work better than the others, in which case that's likely to become your initial model the next time you go around. So the one thing I mentioned in here was the part where we're going to be comparing our model predictions to observed data, and we're going to do that using posterior predictive checking. And that we can at least somewhat loosely break up into two categories here: graphical checks and more formal numerical checks. I'd say the bulk of the methodologies I would use would fall under the graphical checking heading here. So one category under there would be comparing your observed data to model predictions of data and assess whether they're in some sense comparable. In other cases, you may want to compare some summaries of your data to model predicted values of those same kinds of summaries. So for example, the distinction between these two cases here is, say, for something like a pharmacokinetic modeling problem, would be in the first category here where you're comparing data and predictions. Okay, well, your observed data in that case may be plasma concentrations of parent drug, so that would be your data, and you would also make predictions of those same plasma concentrations and assess how well they compare. Alternatively, you may want to compare some data summary, which in a PK context might be something like an area under the curve, or maybe a peak concentration, or the time at which the peak concentration occurs. Well, you might choose to compare one of those to your model predictions. In many cases, those types of comparisons can be a more sensitive assessment of the model performance, and in some cases you may find that some deficiencies are observable in those summaries that were not apparent when you looked at simple comparisons with observed data. And as a result, that might lead to a model rejection, particularly if the inferences of interest are somehow more closely related to that data summary than they are to the ability to predict individual plasma concentrations. And then finally, we have a form of residual analysis under this heading too. As we'll see in a minute, residual analysis in the context of categorical data analysis is a bit different than we're used to in the continuous context, and also probably less valuable to us. I think when we're working in the categorical data realm, generally the first two categories here will be the more valuable ones for assessing model sufficiency. Finally, some of these sorts of graphical checks can be translated into numerical checks by constructing what are sometimes called posterior predictive p-values based on some test statistic. Test statistic may well be one of these very data summaries that we're talking about. And you can come up with a p-value that, if it happened to be particularly extreme, like say less than 0.05 or more than 0.95, that might lead you to rejecting your model. So you can, in principle, construct formal tests then based upon those kinds of numerical quantities. So let's take a closer look at some of these. Let's start with some graphical checks. Now, first, let's consider the case where we're looking at purely binary data. Basically, all our data is essentially zeros or ones. In that case, if you tried to take plots superimposing posterior predictive distributions and your observed binary data, that's not going to be particularly informative. So when you put your posterior predictive distributions, well, depending on how you construct those might take on take on continuous quantities between 0 and 1, but the observed data is all 0 1s, and it's very difficult to assess goodness of fit looking at that kind of data alone. Now, in the context of binomial data, like some of the data that we've seen in some, let's see, I guess the most recent example we were looking at is actually shown here. Depending upon how many, what the sample size is for your binomial data, it could actually look almost continuous in its form, and the same kinds of model checks you would use in a continuous case are applicable in this instance. And that's illustrated down here, where we're looking at plots of the observed and predicted fraction of patients that fall within a given category. So the example here is that one I showed you before, where we're looking at patients where we're trying to prevent postoperative venous thromboemboli. So we're plotting here the fraction of patients with a VTE on the y-axis versus dose. We've got different panels corresponding to the different studies that contributed summary data, again in the form of fraction of patients that experienced a VTE, plotting those versus dose, and then overlaid on that we have a posterior median in blue and a 90% credible interval around that. So we can compare our predictions, in particular compare that credible interval to the observed data to assess how well our model is capturing the behavior of the data in this instance. And recall, in this particular case, since it's a hierarchical or a population model, we've got two categories of predictions. The first one here on the left is our so-called individual predictions, where we're predicting new data in the same studies, or the population predictions on the right, where we're predicting new data in new studies that have the same design. Same design again, meaning same drugs, same doses, same number of patients in each treatment arm. But again, you can look over this, and at least the visual experience I think you'll get from this is that overall the model does appear to capture the observed data reasonably well, with only maybe the occasional hint of something systematic, like maybe in this LY study here, but I think the overall impression is that it largely captures the data. So that's one way of looking at it, where we're comparing our model predictions, and these are model predicted individual data. Well, sorry, I shouldn't even call it individual data. It's just model predictions that have the same form as the data that we analyzed. Another case I mentioned was the idea of comparing data summaries with model predictions or inferences. In this particular instance, the data summaries, in the example I'll show you for the data summaries for the binary data, essentially take a form similar to that binomial data. So again, if we have binary data, now if it's possible to take that binary data and meaningfully group it in a way where we can calculate, say, the fraction of patients that experience a particular event within each one of those groups, we can treat it in much the same way I just showed you for the binomial data. So that's what we're talking about here then. So we're grouping into subsets. So the original data, this, by the way, corresponds to your hands-on example 1. In fact, this is exactly from hands-on example 1, where we were looking at patients that experience pulmonary exacerbation. The raw data is binary. It's either a 0 for patients who experience no pulmonary exacerbation, or it's a 1 for anybody that experiences at least one pulmonary exacerbation. So that's why we've got fraction of patients with pulmonary exacerbation on our y-axis. Plotting that versus dose of what did we call it, MI2 or something, and then it's also been broken out here by whether or not the patients were also taking chronic antibiotics. So each one of these dots then corresponds to a group of patients. So for example, if I take this dot here, I've got a group of patients who had been assigned to placebo and were not taking chronic antibiotics, and I go ahead and I calculate the fraction of patients within that subgroup who experience an exacerbation. And I do that same thing for all of these subgroups. And then when I do my posterior predictions, again, the posterior predictions originally simulated a bunch of individual patients, and I do for each MC sample, I do exactly the same thing as I do with the observed data. I calculate the fraction of predicted, a fraction of patients who are predicted to have pulmonary exacerbations in each one of these subgroups, and then calculate the median and the 5th and the 95th percentiles for those posterior simulations. And again, you can look and you can get a visualization of the extent to which the model does or does not seem to capture the data in this instance. So that's what we're looking at on the left. On the right, you're looking at another representation of essentially the same posterior predictive check, but giving maybe somewhat more comprehensive information. And what I would say, imagine you're going to take one of these points. Let's take under chronic antibiotic here, the 20 milligram group. If I was to take a cross section right up here at the at the 20 milligram mark here, take a cross section of the distribution of posterior predictions. So instead of grabbing only 3 quantiles, I'm going to take the entire distribution of posterior predictions here and plot that. Well, that is, let me make sure I got to see that's chronic, so that's going to be on the right. It's the 20, so that corresponds to what I'm showing here, the one I've just highlighted here. So we've got that distribution is shown in blue here. You can kind of ignore the dots on the bottom. They're actually kind of useless because we've got so many values, but those actually correspond to the different posterior samples that generate this density curve. So I've got a density curve here. You can see it's centered, where are we here? Around 0.2, I don't know, 0.27 or so, which I imagine is probably about where this point is right here. And And let's see, where was I going with it? Okay, so you've got that, and now we can compare the observed data, and that's the observed value is this red dashed vertical line that's overlaid on top of that distribution. So that's just another way of viewing the same kind of information we have on the plot on the left. Again, it's in a sense more comprehensive because it's showing the full distribution instead of just picking off a few quantiles. The other thing I've done over here is actually calculated, I mentioned before, this posterior predictive p-value, and that's what I've done right here. I've calculated well, it's labeled here as the probability of that the predicted value is greater than or equal to the observed value. And you get a value here of 0.356. What that's saying is I've taken all of the posterior predictive values here, which, as I recall, I think we generated like 3,600 values, and I count up the fraction of those which are greater than the observed value here, and that fraction then is an estimate of the posterior probability that the predicted values are greater than the observed, in here that they take on a value greater than that observed value. Now, what I'm looking for in this is to see whether or not I have a problem where these values tend to be extreme, either much less than 0.5 or much greater than 0.5. Some people might put a formal test on it. They might say, okay, I'm going to reject this model if that value is, say, less than 0.025 or more than 0.975 or something like that. But whether you do it as a formalism or just as or just to get some idea to sort of reinforce the graphical presentation of whether these things are in extremes, it can be a useful number to sort of indicate to what degree the model is or is not consistent with the observed data. In the particular example we're looking at here, none of the values are particularly extreme. I think the worst one we have is where, probably up here, this 0.814. And that's certainly not too bad, and it's not enough to argue that the model needs to be rejected, at least based upon this piece of evidence. Okay, that's about all I was going to say about the more typical posterior predictive checks. What I was going to talk about next is doing residual analysis when we're dealing with categorical data, in particular binary data. Oops, boy, did I jump the gun there. Okay, there we go. Oh, not quite. Okay, so I want to talk about another category of graphical checks, specifically residual analysis, and a few comments before we jump into it. First of all, conventional residuals, where we take our observed value minus an expectation based upon the model, are not as informative or intuitively interpretable as they are for continuous data, and that's particularly when we're dealing with binary data. If we're dealing with binomial with a large sample size, these are probably reasonable. But with straight binary data, they're pretty limited. You've got this one quantity, the expected value, which is going to be a nice continuous number between 0 and 1 in the binary case, but y is always 0 and 1, and the end result is you've got sort of an odd-looking creature that doesn't let you really assess model fit very well. As a comment here, there have been a number of alternatives proposed for this kind of categorical analysis, and you'll see terms in the literature like normalized, adjusted, or deviance residuals. And just also comment that in the Bayesian context, when we talk about residuals, keep in mind our predicted values are actually distributions. They're not just point estimates. So because those are distributions, then when we take our observed data and subtract those those predicted values, the resulting residual is also has the form of a distribution that reflects the uncertainty in our model predictions. So let's get more specific here. Let's pick a particular context here to work with. Well, first, I guess a general comment is that it turns out that in the binary case, residuals are useful for outlier detection, but as I say here, but not for much more. In particular, they're not particularly useful as an assessment of model fit. But occasionally they can be useful for identifying outliers. So let's make a context to study these. Let's assume a logistic regression model for binary data, such as the type we've been using up to now. So we're going to have our observed data, our yi's, are going to be distributed Bernoulli with some probability, pi, and the logit of pi is going to be some function of our covariates and of our model parameters. In other words, our xi's and our thetas. I'm going to base my discussion mainly on a paper by Albert and Chibb, who proposed two types of Bayesian residuals. Also, I give you the reference for that paper. In addition, if you look in the Gelman et al. Text that I cite in the references at the end of the slides there, that's actually where I picked up on this, and they spend some time talking about it too. So they propose two types of Bayesian residuals. One is they term response residuals, and the other they term latent response residuals. So let's take a look at those. First of all, the response residual is pretty much what you would think of as a residual. We're going to take our observed values, our yi's, and subtract from them the expected value of that yi, which is exactly that pi value from our logistic regression model. And we can go ahead and we can plot the posterior distributions of those residuals, and we can use them as the basis for detecting outliers by identifying those individual data points that have absolute values greater than some specified value. One problem with coming up with that specified value is that it turns out that these sorts of binary response residuals do not have a known sampling distribution, so it's hard to identify a critical value based upon probability. So it's hard to come up with a really nice, rigorous critical value based upon probability theory. But nonetheless, they are done sometimes. Now the other category that they suggest is termed a latent response residual. And this is based upon a particular so-called latent variable interpretation of the model, and we can use that to construct it. So what we're going to do is write the model in a different form, but equivalent. So instead of writing the model as we did, let's just skip back here. So recall here we've got our yi as Bernoulli, and then the logit, well, it's Bernoulli with this probability pi, and the logit of that probability is this function f. Well, let's take that same function is going to come into play, but we're going to write the model differently. Our observed data is written this way. So we've got our yi is going to be 1 if our latent variable zi is greater than 0, and yi will be 0 if that latent variable is less than or equal to 0. And our latent variable is just the same function we talked about before. It's the same f plus some error term, epsilon I, where this epsilon I has a logistic distribution in here. Well, it turns out that this is precisely equivalent to the model that we just talked about. So it's the same form of the model. The difference is the way we've written it, and the type of residual you can construct out of this is, instead of constructing the residual about the observed variable, we construct it around the latent variable zi. So that's what we've got right here, and it's equivalent to that epsilon I term, which is the difference between zi and this f. The f, again, is also the expected value. In fact, it's the expected value both of the... oh, actually, I was about to say something wrong, wasn't I? Let's see. Yeah, I was about to say it's the expected value of y, but that's not true. But it is the expected value for the zi. So we're going to construct those. I suppose the advantages to this are, I guess, one is now our residual, both the zi and our predicted value here are continuous. And one of the advantages from a formal probabilistic point of view is it turns out in this case that epsilon I has a known sampling distribution, and if you have a known sampling distribution, you can construct formal probabilistic tests where you can choose to say accept or reject something based upon a formal probabilistic criteria. So we can actually construct the posterior density of these epsilons using our posterior distribution of our function f and the known distribution of epsilon given f. And I'm not even going to go through this in any big detail here, just to point out that it's the distribution of that epsilon then is known, and it has the form we see on the right, which involves a combination of a couple truncated logistic distributions in here. And once we know that, we can construct formal criteria for accepting or rejecting whether or not something is an outlier. And that's what I was saying here. The resulting latent response residual then can be compared to the quantiles of the standard logistic distribution. Another advantage to this approach is that it's more readily extended to ordinal data, which we'll be talking about in a little bit. So it's a more generalizable approach if we go to the latent response residual. But we're still talking about something that's not very informative about model fit. It's largely useful as a method for assessing outliers. So what do these things look like? Again, I've taken the hands-on problem 1, same data we were just looking at. Looking at here, you can see the data again broken out by, in this case, by dose group, the 0, 20, 40, and 60 milligram per day dose groups, and also divided up by, in this case, not completely divided, but colored based upon whether the patients were taking chronic antibiotics or not. And I've plotted the residuals. So in the left-hand set of panels here, we're looking at the so-called response residuals. And here the y-axis is the residual value, and it's been plotted in this case versus the expected probability on here. And you can look at these. In this case, for reference points, there's the 0 line is marked. In addition, plotted the minus 0.75 and 0.75 value here. Those were values that Albert and Chib mentioned as possible markers for whether or not something was an outlier. Though it was pretty much a heuristic. It wasn't anything that there was a real formal basis for it. But what you're looking at, now keep in mind, these are always going to be again, that's going to be our yi minus the expected value. So if your yi is 0, you're always going to be down here below the 0, and if your y is 1, it's going to be up here above 1. That's why you always have this 2 groupings here depending upon whether the observed value was a 0 or a 1. And about the only thing this is useful for is to see if you have any particular extremes. And you can see there's a few things wandering up here above that 0.75 mark. Again, without having a formal probabilistic basis for this, it's really hard to say if any of these are really problematic. There's a couple of them here, this one and this one, which are kind of separated from the rest of the data that might be suggestive of it being an outlier. But again, there's no formal probabilistic basis for rejecting it. On the right-hand side, we're now looking at the so-called latent response residuals. Again, you're going to get two groupings in here based upon whether the observed value was a 0 or a 1. The 0 value is down below, the 1's above. So they're still going to break out based on that. Again, we can, and I guess I forgot to mention, these things that are the error bars on here are actually represent the 90% credible intervals for the residuals in here, and we can look across those. It's a similar kind of story, except now the bars that are on here, the extremes actually correspond to probabilities of 0.025 and 0.975. So now you've got some probabilistic interpretation on these, and then we've got no really gross outliers, but again, you could probably argue that some of the extremes where the credible intervals are, are going over, over the line, and again, where that is separated a bit is at least suggestive. We might be able to argue that those couple of points are arguably outliers in this group. But again, that's about the only thing I find it useful for. Let's see what was going to be next. Okay, now let me take a breather and see if there's any questions here. Just so that you know what I was going to do next is I was going to actually step through a little bit of the code for how you can generate some of these posterior predictions to give you some, at least something that you could use as a template for future work. Okay, so far nothing popping up, but I'll keep my eyes open here. Let me actually, we're going to step back to the example we were looking at here, which comes from your hands-on problem 1. And what I was going to do is show you that code and point to at least some of the elements in that, so that you've got some basis for beginning to understand the code and maybe having some sense of how you can use it for other problems. So we're going to look at how you would actually generate these kinds of posterior predictive checks. Okay, computer's being kind of slow there for some reason. Actually, let me see if there's something going on I need to change. Something's busy. Well, it's just the GoToMeeting. Okay. Well. Okay. So you've actually got this code already, because in the solution I provided for hands-on problem 1, the code's already there. What I have done, though, is I realized this morning I did a pretty lousy job of annotating it. So I've put some additional annotations in here, and I've posted the annotated version on the course website, so you can get it there. But let me go ahead and open this. Okay, let me make it bigger and make the fonts a bit bigger. Okay, hopefully that makes it reasonably visible. Let me know if you're having any trouble reading it. Okay, so the first part of the code is exactly what you saw before. I want to take us down. Oops. Take us down here. Let's see. Yeah, right here. Okay, how did this all jump? Oh, I see what I did. Excuse me while I get this back where I want it. Okay, just wanted to get back to that screen. Oh, not that screen. Okay, so we want to look at how we're going to do these, and let's start with the one on the left-hand side. So again, this is the code, and the only difference between this and what you had before is annotation. So you'll see more. You'll just see more comments embedded in here. So this is where we start out by first of all grabbing the our posterior matrix, which has all of our MCMC samples in it, and just grabbing the subset that contains our predicted values, which I had called EXAC pred. So that's our predicted, our predicted exacerbation occurrences there. Again, that's our binary. It's simulated binary data in this case. And the first step I go through in here is I'm going to calculate the fraction of patients with a binary exacerbation in each treatment arm and antibiotic use subset. So I have to break out the data by both dose and by whether or not they're taking antibiotics, and that I do using the R aggregate statement. So all this is saying is, okay, take the. By the way, this is for the observed data in this line. So for the observed data, it's grabbing that, and that was in a data frame called data prob 1. So it just grabs that, takes the exacerbation column, tells it break it up by dose and by antibiotic use, and calculate the mean. In this case, when you take a mean of 0, 1 binary data, it actually gives you then the fraction of that have values of 1, and then just a little bit of housekeeping after that here, where I just need to convert dose back to numeric, because aggregate has the bad habit of converting all of the things that it subsetted by into factors. So I convert that back to numeric, and I create a new column called type, which will be observed for that case. Then what I do is, the next thing here is I do exactly the same thing as I just did for the observed data, but I do it for each one of the MCMC samples, because for each MCMC sample I simulate an entire set of observed, observed in quotes, I guess, observed data values. So I have to go through the exact same process I just did with the observed data, but do it for each one of those samples. And then sort of all in one go, I do that, and also I use the quantile function you see here to generate the fifth. You can see here I'm generating the 5th, 50th, and 95th percentiles of that. So that's the way I get my posterior medians and my 90% credible interval. And again, that's all done inside this one statement right here. So I probably should have broken that up to make it more readable, but that's basically that one statement is doing the same thing we saw up on top as that aggregate statement, but it's doing it for each one of the MCMC samples, and then once it does that, it also calculates then the quantiles for that. And again, we do a bit of bookkeeping where I create that type variable where now instead of observed, it's going to be the 5th percentile median and the 95th percentile. And then I put both the observed and the observed data as well as those quantiles together. And then I do some plots. Oops, just jumped the gun. Let me get back there. Okay. Okay, it's not behaving on me. There we go. Okay, so you can see here's the comment here. So I'm going to plot the fraction of patients with pulmonary exacerbations versus dose, where I'm going to overlay the posterior median and 90% credible intervals over the observed data. And I see I can't spell. Okay. And I did that a couple of different ways. The first one puts everything all on a single panel, which is not what I show here, but that's, in fact, I can show you what that looks like. Let's see, which one of these is that? Oh, wrong place. Okay, so that's where I overlaid everything on a single panel, and I just colored the case with no antibiotic blue and the ones with antibiotic red. So that's what you get if you plot it that way. So that's the first case here. So I'll let you, if you want, you can go ahead and explore how that's done in here. But the main thing you'll see is I'm plotting exacerbation versus dose, and then it's this grouping over here where I combine both the type, which in this case is observed, or the various different quantiles, and antibiotic all in one. So I end up with essentially six different curves in there. And then the other way of doing it is where I instead break them up into separate panels, and that one looks like this. It's the same thing, it's just broken out two different ways, but if you want to explore different ways of playing with the lattice graphics, that'll give you some idea. Okay, let's scroll on down. Okay, and then the next set of code in here is the one that was used to generate, let me go back to the slides here. Is the one that was used to generate the panels you see on the right, where we've got the densities plotted with some of the other stuff overlaid. In a sense, this falls under the heading, I guess, of advanced lattice use, but you might find it useful to explore. So, but the first part of the process is similar. I go ahead and calculate the fraction of patients with exacerbations for each arm and antibiotic use subset, and do that using aggregate. So that's the same story as before. And then I do the same for each of the MCMC samples. The code's a little bit different because in this case I'm not going to be calculating quantiles. I actually want to generate all of these posterior predictions and calculate these fractions for each one of the MCMC samples and then keep it. I don't want to summarize it using quantiles, because I'm going to use that information to construct these densities. And then down here, you can see the comment here. So now I'm going to plot the posterior density of those predicted fraction of patients with exacerbations for each dose and antibiotic use subgroup. And then on each one of those panels, and this is where the advanced lattice stuff comes in here, is I'll also be overlaying a vertical line that shows the observed value, and then calculating the fraction of predicted values that are greater than or equal to the observed value, and adding text that shows that value. So the core thing then is to take is to use the density plot function from the lattice plot package to plot the model predicted exacerbations. So that's why if you look here, you'll see the data is x2, which happens to be what I generated up in this section. So that does not involve the observed data. So I do that. This mess here is just telling it to break out it into panels by both antibiotic use and dose, and then some fancy bit to get the labels that I want on it. Then where the advanced stuff kind of happens is down here within this panel function. And again, I don't think could at one sitting probably go through this in detail without knowing what your background is on using lattice graphics, but just point out that this section here is the first panel statement inside of it generates the density curves, but all the rest of it here is used to generate that vertical line for the observed data and to generate that posterior predictive p-value. So I'll let you peruse that probably on your own to see if you can make sense out of what I've done there. If when you get done you do want to ask questions about it, certainly feel free to do so, and I suggest using the forum section in our website to do so. So that's really the core then of generating the two plots that you see right here to do our posterior predictive checks there. You'll also see when you dig into this, I also do essentially the same thing, where instead of breaking it out by, oops, what did I just do? There we go. Okay. I instead of breaking it out by antibiotic use, I break it out by rhDNase use. So, but it's the same idea. And let's see, let's scroll on down to the residual analysis, which was the other part we talked about, where I was looking at the two classes of residuals. I'm going to do both the response residuals and the latent response residuals. So the first part in here, I refer to them, I guess, in here as standard residuals. That's the same thing as what I was calling response residuals in the slides. So first thing I do is again go out and grab, well actually in this case instead of grabbing the predicted values initially, I'm grabbing the predicted values not for our binary data but for the probabilities of exacerbation. So that's why you see this p-exact in here. So I'm grabbing that, then go in and get the observed data. And I'm going to calculate the, let's see, where are we here? This is, okay, yeah, this was just getting the observed data. This one is taking those predicted probabilities and getting an average. The only reason I actually do that is that'll serve as our x-axis in our plots. Okay. Okay, so we do that, and then I calculate the residuals. So that's right in here. Well, I calculate actually the 5th, 50th, and 95th percentiles of the residuals. So that's all that's going on here. You can actually see embedded right over here is where I take the observed values for exacerbation and subtract from it the predicted, our predicted values. Or in this case it's really our probabilities in here, and that's all embedded inside of calculating the quantiles of those to get our posterior median and 90% credible intervals. And then I just stick some labels on that. I then pull that together with the observed data, and then I do those residual plots in here. What was I looking for here? Yeah, I do our residual plots. This one I do use an extra trick in here. There's a function, I think I included this inside the Beagle SB Utilities file that I've provided you. And I'm trying to remember the fellow that actually developed it. I didn't develop that particular function, somebody else did, but it is contained in there, which creates plots that include error bars on them, or the CI actually stands for confidence interval, shown as error bars, so that we can see the our posterior predictive intervals in that. But the core here is it's just an XY plot, and that's, let me go back down to our pictures here. Okay, so what I've just done with this XY plot statement here then is generated the plot that you see on the left in here. So that was the relatively simpler one once you have a hang of how to use the plotting panel here that shows the error bars on it. It gets a little messier when we have to deal with the latent residuals, and you can see those beginning right at this line here. And I have to do a little stuff up front here. In particular, I need some functions for the truncated logistic distribution, because those are not built into R, so we go ahead and build some here. So they do have a logistic distribution, but we had to make separate functions here for the truncated logistic distribution. So we got functions here for the inverse cumulative distribution function, something that generate random variables from the truncated logistic, a density function, and a cumulative distribution function. Then we go through a process similar to what we did before. In fact, the first few lines are identical to what we did before here, where I get the observed data and calculate the means of the posterior probabilities for exacerbation. And then the residuals get calculated in this mess here. And what you're looking at in this section is going through and stepping through all of our posterior samples and doing what you see in the slide right here. So this relationship that you're seeing, where it's dealing with the truncated logistic distribution, is exactly what's happening inside this set of code right here. And then it calculates again the 50th, and 95th quantiles of that in there. Again, pulls it together with the observed values, and the code here is essentially identical to what we had for just the standard response residuals, and the end result is what you see on the right hand side. So I encourage you to actually go back and look at that from problem 1, because that's where this example is coming from, and so that you've already seen that, but now you can see some additional things you can do with it. It's definitely another point to take a breather, see if there's any questions. Okay, so far nothing cropping up. I'm going to keep my eyes open here, and we're actually at kind of a logical transition point because we get into a new topic next, and maybe I'll just sort of point you towards it. Let's see, do I want to? Yeah, I'll just briefly mention the kind of problem that we're going to be talking about when we come back to this next time. But it probably doesn't make sense to jump into substantial amount of content yet. So the next topic's going to be looking at the modeling of ordered categorical data, or often referred to as ordinal data. In fact, usually because I'm lazy and don't want to use all those syllables, I'll usually call it ordinal data. So here we're talking about cases where, well, in fact, here I'll just actually use the information I have here. So suppose you measure some response in terms of an ordinal scale. So, for example, pain measurements might be reported as something like none, mild, moderate, moderately severe, or severe. And often such measurements get reported on a numerical scale, such as the integers 1 to 5, or in some cases 0 to 4, or something like that. So we're talking about a situation where we have it's a categorical scale. So the result can only take on a certain number of discrete values. In addition, it's ordered. So we're talking about things that vary in some quantitative sense. So where you've got a scale from from bad to good, bad to worse, whatever. There's some order inherent in the nature of the values. Now that would be different than, you might have a categorical outcome sometime where it was simply a matter of choosing between a group of options that don't really carry any real order to them. I don't know. I should have probably thought of an example of that off the top, but I don't have one right off the top of my head. But in other cases, you may have something categorical where there's more than two possible outcomes. It's not binary like we've been talking about, but where there's no real ordered value associated with them. But here for now, we're going to be talking about the case where they are ordered, and thus we call it ordinal data. And that's the kind of data we're going to be modeling. The approach we're going to be using for the most part is what you see here, what are termed cumulative logit models. And the basic notion behind the cumulative logit model is we really convert these ordinal measurements into a collection of binary outcomes. And I see I was supposed to have a bullet right here. I'll correct that in the next version. So we're going to really convert things to a sort of a collection of binary measurements. And one particular form of a cumulative logit model for an ordinal scale is shown here. So imagine we've got an ordinal score where the values are going to be numbered from 1 to capital M. And when we write that model, we can write it like this, where our data, our yi, is going to use this categorical distribution with a vector of probabilities. So P is going to be a sequence of probabilities, so it's going to be M values there that sum to 1. They depend upon some parameter and some covariates. And the mth one of those, we could write here then as representing the probability that y equals m. But we can also write that same one as the difference between some probabilities written in terms of inequality. So we'll talk in terms of the probability that y is less than or equal to some m, minus the probability that y is less than or equal to m minus 1, and that equals this probability, the probability based on the equality. And then what we can do is in effect model each one of these inequalities as a binary outcome. So you've got a y is either less than or equal to m, or it's greater than m. And you can treat that as a binary outcome and model that using logistic regression. And that's exactly what we're doing right here. And in the classic cumulative logit model, the only thing that differs with M across those what turns out to be M-1 binary outcomes is going to be the intercept term here, alpha M. So, and that's what I guess I'm saying here, where I say thus the cumulative probabilities of the ordinal scores share a common model except for the intercept, which is unique to each one of the possible values of our dependent variable. So what we're going to be doing then, I guess we probably will talk about this on Monday, is we'll go over this. I'll repeat this slide, and then we'll go on to see how we can analyze that kind of data using this style of a model. In the meantime, I guess if you haven't already done it, continue on with the hands-on example 2, and that's what we'll be going over on Thursday. And I guess I'll see again if there's any last questions before I disappear. Okay, looks like a quiet group today. Okay, well, I'll look forward to talking to you again on Thursday. Bye for now.